Recall, today I want to implement a very simple neural network in order to introduce some nonlinearity into a data-driven instrument. This builds off of some of the ideas I've been working with in other videos with artificial neurons and artificial neural networks. I'll link those in the description, but don't worry if you haven't watched them, this is a fine starting place too. I'm going to be working in MaxMSP today. Since I want to keep our focus on the transformation of the data rather than how we get data in, Max is an easier starting point for gathering mouse data or data from USB devices. Why would we want to do this? Well, you may not want to, and that's fine. If you're happy with a linear mapping of your input data to output parameters such as pitch or amplitude or whatever, that's great. That linear mapping is going to be way more predictable. However, if you're interested in more unpredictable, chaotic behavior, the nonlinear behavior of the neural network could be something attractive for your data-driven instrument. As I always say too, co-opting ideas from new and emerging technologies allows us to regain some ownership of these technologies that are affecting our lives, and perhaps gives both artists and audiences a window into better understanding them. Again, my usual disclaimer that this isn't really machine learning that I'm doing here, but what we're going to do is we're going to make a super simple neural network from scratch to add some chaotic sophistication to our musical input and control. Alright, so here's my MaxMSP window. Of course, you can do this in whatever software you want. The reason I'm doing it in Max today is I want to take advantage of this mousestate object. There isn't really anything akin to this in pure data, and this just gets me mouse information. So if I open up the help here, we can see it's polling my mouse, and it's giving me the horizontal position, the vertical position, the horizontal delta, vertical delta, and if I click. So you know what, just to help us out here, I'm just going to steal all this. Looks good. Hold down Shift, Command C, close it, Command V. Ah, there's our friend. So of course you could get your data from anything. I'm just using this because likely you have mouse input on your computer, but you could use in Max the HI object to get different information from joysticks and things like that. Let's not worry about delta values today. All right. So the other thing that's useful in Max is this scale. Map values to an output range. And so what's good about this is this does a linear transformation for us. So let's just start pulling here. So I think my mouse will go off the viewable screen here, but all the way to this side, the horizontal is 0. All the way to this side, let's stretch this out so we can see better. 1280, 0, 800, 0 to 800. And so we could take now, we know that horizontal position goes from 0 to 1280. So I could take that 0 to 1280, and I could scale it from 0 decimal point to 1. So if I run this in, remember in Max, it differentiates between floats and integers. Okay, so now 0 all the way there is 1. This makes sense? All right. Let's put in a speed lim. This slows down how the data goes through, so we'll make it every 10 milliseconds. Even that's going to be pretty fast, I guess. Maybe I'll make it 50 or something like that. Let's take that and then scale. We know it goes from 0 to 1280. Let's scale it to 20 to 108. That's the range of a piano keyboard, right? 0 to 127 would be our MIDI notes. 20 to 108 would be a piano keyboard. And then we can go and run that to a make note. I don't know, we'll make it at velocity 127, a duration of, what do we have, the speed limit at 50, so we'll make it a length of 40. And then we will run that into a note out. Make. Okay, does this all make sense? I've done this in another video. I'll link that here if you need a review. But all I've done is I've taken the X position of the mouse and I've mapped it to the keys of a piano. Lowest, highest. If I wanted to, I'm going to go ahead and disconnect that for a second. If I wanted to, I could do something similar on the other end too. So I could take this speed limit on the vertical and I could add these together. Bink, bink. Let's see what's going on out of that. All right, so now we're taking our 0 to 1280 and adding it to 0 to 100. So I should have 0 if I'm here, and then 2080 there, 1280, 800, right? So then I could take this scale 2080, lowest here. And so now I've sort of clumsily mapped this to XY space. I've made them interrelated. It's still linear, going this way and that way. All right, so this is our linear data-driven instrument. Again, I'm not going to win any awards for this instrument design, and you could probably immediately think about new ways you might have velocity changed by this. But we wanted to start with something simple, so now we can take this simple concept and use our artificial neural network to transform. All right, so let's make our artificial neuron. And pardon a bit of my clumsiness in Max, I've gotten too used to pure data. But what we want to do is we want to create a subpatcher, and we'll call it Neuron. If you've watched my artificial neural network in Pure Data video, you know that in Pure Data we created a separate file for the neuron, but this P now gives me a little subpatcher that I can make here. To review, a neuron is just a mixer and a nonlinearity. So here we go. This addition is going to be our mixer. Notice that I'm not adding tilde because I'm not going to add audio signals. I'm going to add these data signals. And then underneath that, let's put in a tan H, which is my go-to nonlinearity. And that's it. So now we just need a couple things. We need an outlet, because we need to get this information out. And then we need, let's do 3 inlets. There we go. What's going to happen to these inlets? Well, we need to weight them, right? So we need to be able to change how much they influence the neuron. So the way we'll do that is with a multiplication. And then that runs into the addition. Actually, I'm going to delete these for just a moment. What are we going to multiply it by? Well, let's create a way to randomize this. And if you've watched my other videos, you've seen this before. Let's create a button. Well, actually, before our button even, let's do a receive, randomize. So this is going to get a bang that randomizes that. And then we'll choose a random number. Choose a random number up to 200. So again, that's between 0 and 199. Multiply it by 0.01. That's going to give us from 0 to 1.99, and then let's subtract 1. And again, careful to put the decimal point in there. And that should give us a number between -1 and 0.99. Look this up. Hit the randomize. Seems to be working. Okay. And so we will have that be the weight. And so now let's take this, duplicate it, duplicate it. So now I need to make sure I can add these all together. So let's do this, think. Those two get added together. All three added together. Command Y to clean up my wires if I want. 3 inputs. I can randomize the weights of them. They get added together and then run through the hyperbolic tangent. So again, the hyperbolic tangent is our nonlinearity. It makes it so that the result of this is no longer linear. And by having our individual neurons nonlinear, we make it so that it can't be simplified down into a single linear function, right? And so when we start networking 3 of these, 9 of these, we know that each individual neuron is actually playing a role. So this is my neuron, and now it's going to be pretty easy to do stuff. Let's think, though, if we're working with hyperbolic tangent, we need numbers that go from -1 to 1 from here. So let's do a conversion here. Scale. Again, we know that our horizontal is 0 to 12/8, our x position, and then we'll scale that to -1 decimal point, 1 decimal point. If you forget those decimal points, which I often do, this could stop working very quickly. Okay, that's looking good. Move this friend a little bit higher up. Let's stretch it out. Because I'm a bit clumsy in Max at the moment, I'll probably speed up my adjusting of things in the video here. All right, let's duplicate this. We need a different range of numbers here, though. This one needs to be from 0 to 800. So Y position, -1, 1. Great. So we've got everything all scaled nicely. Command Y to line things up a little bit nicer. So now, at the end, we're going to have to scale it back from -1, 1, and we'll keep our piano range there, 20 to 108. So now I could send these 2 into the neuron, run that out. That's a whole lot of one note at the moment because I haven't randomized these yet. So let's make a big old button here. And let's send randomize. So now let me open up this neuron. So now when I click this big old button, whoops, it's now randomized my weights here, right? Okay, so now let's listen to that. I've made a mistake. And it's the mistake that I always make in Max. Everything needs to be told that it's a float, right? So what I'm putting in here is a 1 decimal point. And so if I don't, these are trying to multiply integers, these are trying to add integers, and we just get a whole bunch of sadness. Oh, now we can see here. All right, now we get some numbers that are actually looking a little bit more interesting. Randomize. Randomize. They're still not looking that interesting. All right, let's wire this up and see what we got. All right. It's not happy when I don't use all the inputs of the neuron. I was planning on doing that later anyway, but just to show I've run in the horizontal position twice. It means it's going to be weighted in a different way in our neuron, but that's okay. This is neat. Already, this is now a nonlinearity. So now I'm going to disconnect this so I can talk. We take in those 2 inputs, the horizontal and the vertical. I scale them to be -1 to 1 because that's what our neuron wants. It adds them together at different weights here. Oh, that's very heavily weighted there, and that's heavily weighted in the other direction. That's interesting. So they're almost canceling each other out. That's a lucky roll with my randomize. Oh, and now they're down to trivial ones. And then I use tanh to make that nonlinear. I'll throw in an image of what the tanh does. Again, it just as you approach -1 and 1, it sort of rounds things off. So again, a linear function would be the straight line, but this nonlinearity we introduce to it gives an unusual characteristic. Okay, well, so this is a neuron, but let's make a neural network now. So let's go to duplicate, duplicate. Okay, so now for this one, I'll do 2 Ys. And by the way, I could be taking the delta vertical or something for that. And then for this one, I'll do 2 horizontal again. Command D to duplicate. Command D to duplicate. We'll start with a 9 neuron brain here. So now I'll just take each of these neurons and I'll run them into every neuron. And this one, same thing. Again, not the most sophisticated neural network in the world. Let me take one more neuron to add things together. And by the way, it's going to sound like rattling on one key. No, it's got a little bit of wiggle in there. But we haven't hit randomize for all these new neurons yet. I'm going to slow this down a little bit. Got a smaller range going on there. That one's got a bigger range. The vertical position seems to have a big effect on this one. And when I say this one, I mean this set of random weights that I keep randomizing here. So again, all of these neurons have their own individual weights in there. And since each neuron ends with a nonlinearity, there's no way to simplify this down into a single linear function. Just to disconnect that for a second, we could make the mouse button randomize for us. Tog edge. And so this is just basically converting this toggle. So now when I click the button, that happens. You can hear the space as I move across is no longer linear. A lot of notes close together there. Then all of a sudden it starts jumping into leaps on the right side of the screen. Click it again. Not a lot of range in that one. That one's not very interesting. Let's randomize them again. There's an interesting one. So not every set of random weights is a winner here. A next step, which I won't get into today, would be to, as always, look for the bright spots. So in rehearsal or creation of the piece, I can keep randomizing values until I find ones that I like, and then build a way to save those values. Then if I end up with 4 or 5 sets of weights that I like and I've saved, now I have 4 or 5 different ways to interact with my instrument as I've developed it. Now, If we want to make this more interesting, let's now add some feedback. Send feedback. And we'll take the feedback out of the neuron. Receive the feedback. Let's put on a pipe, so this delays the numbers coming through. And since we've got our speed limit at 100, let's delay the feedback for 100. And then let me do one more thing. Again, negative feedback is often more interesting than positive ones. So times -1 point. And so again, I'm doing this before I scale it back. So it's, again, -1 to 1. Just do a way to keep an eye on that. And now, instead of duplicating this, let's send the feedback signal as our third signal in each of them, right? Oops, deleted the wrong wire here. Vertical, right? So now all of these neurons are horizontal, vertical feedback. All right, let's see what this does. That's an incredibly dull one. Looks like I have a mistake here. There we go. Ooh, that's a nice one. That one has a really interesting area around here. Just by introducing that feedback doesn't mean this is machine learning. Arguably now this artificial organism is reacting to itself. So it's a cybernetic system. And again, if you want to move away from linear transformations of your data, this is a great way to introduce some non-random chaotic behavior. All right, I haven't decided what I'm going to do yet, but I'm going to take this one step further and make a slightly more sophisticated data-driven instrument, which I'll transition to here. In the meantime, give this a shot. Let me know what you come up with.